intuitively. Let's go back to what we know already about sample distributions, about population distributions and sample distribution. We had a couple of questions online while the lecture was going on as well. Let's say that we have a population, okay, and that population consists of, I don't know, a lot of people say 1 million people. There are 1 million subjects that are in our population. And we draw let's say it's a normally distributed population. We draw our distribution as a normal distribution, right? A lot of different values in here. So we're drawing it as a smooth curve instead of a histogram. And we know that one of the properties of a normal distribution is it's symmetrical about the mean and the median. I'm going to say, for argument's sake, that we know the mean of this population, mean is equal to 200. We also know the standard deviation, the variability of standard deviation for this population. That's equal to, let's say, 20. Okay, so what does this look like? With this population that we've described with these two numbers here, that's just those two numbers there give us a good idea of what this population looks like, how these 1 million people are distributed. We know the middle is around 200, and we know that this number 20, sigma, standard deviation of the population, gives us an idea of how spread out the values for this population are. Let's say that, for argument's sake, that this is total cholesterol, for instance. Okay, so they eat a lot of cheese, and this is Michigan, I guess, right? Or cheese in Michigan. Which team is it that has the Green Bay, right, with the cheese heads, right? So at any rate, so let's say the average cholesterol for these 1 million people in Michigan is 200, and standard deviation is 20. So right from that, we know that if this is really a normal distribution, a very large population like that as well, we know that 95% of the people in this population are going to have a cholesterol between 160 and 240. And how do we know that? We know roughly between those two numbers. How do we know that? Because we know in the normal distribution, using the empirical rule, that if you're 2 standard deviations below the mean, 2 standard deviations above the mean, those values represent the range for 95% of the population. 2.5% are going to have cholesterol below that, and that leaves 2.5% at the other end, so 2.5% are going to have cholesterol above that, right? That's when we're dealing with the population. Well, the problem is that we never get to see this. We never really know that, right? Just like, I don't know, did you tell him your age, Levi? Oh, too bad. So you could have said, I'm not going to tell you my age because, you'll just have to know what you know about it from the confidence interval, because that's really where we wind up, because we never really find out what the mean of our population is. We only know what we know from our sample, right? So let's say we take samples from this population, but we don't just take one sample. We take the same size sample over and over again. I'm going to say, for argument's sake, that sample size is 25. We take that same size sample over and over and over again. Each time we take a sample of 25 people, we average those 25 numbers, and we write it down. We do it again, we do it again, we do it again. If we do it an infinite number of times, right? Just do it constantly an infinite number of times, and we take all of those results. We know that most of those results are going to be closer to the mean than these individual people are, right? So in other words, if the lowest total cholesterol for anyone in this population is 120, right? We know all of those means are going to be greater than 120 because you got to average 25 people in order to get a sample mean, right? So if there's only one person 120, then you'd have to have that'd be averaged into 24 other values. So we know that the range of these values is going to be tighter than the range of the population. And we've learned that that's predictable, right? If we know the population standard deviation, the thing I just lied about right over here, that we knew it, we know the population standard deviation, we could predict that the spread of this new distribution, which is all sample means, has a value that's smaller than sigma, tighter than sigma, narrower than sigma. And it's going to be equal to sigma divided by the square root of the sample size, which kind of makes sense because that means the bigger the sample size is, the closer all of those samples are going to be to the mean of the population, and the tighter and tighter and tighter the spread is going to be. So if I took samples of size 25 over and over and over again, right? Well, now my new standard deviation is going to be equal to 20 divided by the square root of 25, which is 5. It's going to be equal to 4. So my samples that I take over and over and over again are going to be the same mean as my population, 200, right? That's intuitive, right? Because you know half times you're going to get sample more or less than the mean, but they're going to average to the same thing as the population is going to, especially if you take an infinite number of samples, it's going to have to, right? So, but the spread is going to be narrower. So in this case, our spread now are 95% interval. 95% of these values are going to be between 2 standard deviations above and 2 standard deviations below, which now is going to be 192 to 208. Well, what does that mean? What does that mean, that range? That means that 95% of the samples that I take of size 25 from this population are going to be between 192 and 208. So here we're dealing with the sample means, and here we're dealing with the population values themselves, right? And here our mu is approximated by the mean for our repeated samples, but sigma, well, that really now has changed, right? Now that's equal to the standard deviation for these samples is going to be equal to sigma over the square root of n. So I don't want to call it standard deviation anymore. I'm going to call it the standard error instead. But it's a standard deviation, just standard deviation of the repeated samples that you've taken. So that's a new distribution, right? So that's important to us, right? So now the problem now becomes, and I'll tell you what, but before we go move on from that, let's do an example. And the way we usually wind up applying this, in my cursor, there it is. Oh, that doesn't matter which one I open. Okay. So the way we usually wind up applying this is that, well, we go take a sample, and it turns out that we don't know anything about, we don't know what the population mean is. And let's say that I happen to tell you that we know that the population standard deviation is equal to 20. And I'm going to use the same values as before, right? Say it says population standard deviation is 20. We don't know the sample mean. Is there really situations where we know that? Probably not, right? There are situations where we may rely on an older study that was had a very super large sample, you know, maybe not the whole population, super large sample, where we think it's so big that we can make believe that we know the population standard deviation. That might happen occasionally, but I'm just, for our purposes right now, I'm going to make believe that we actually know what the standard deviation of the population is. That's sigma. Okay, and I'm going to say, okay, I'm going to go into this population. I'm going to take a sample of size 64. Okay, so I take a sample of size 64. Okay, and it turns out that the mean I get from size 64 is equal to 202. So now that's all I know about the population. I took a nice big sample, size 64. We had a little debate about what's a large sample, what's a really large sample, what's a kind of large sample, right? So the large sample, we maybe start defining a large sample at about, say, 35, and it's 35. And really, if you want to be a little bit more conservative, you might say maybe 100. So somewhere in that range, we start to call it a large sample. When we take a look at the T table, you're going to see where you are in terms of how inaccurate you are by using 35 as a large sample size versus how inaccurate you'd be if you use 100. How much of a compromise you're making to use these different sample sizes. It'll be kind of obvious once you see those, once we look at that table. Okay, so what do we know about this population now? We know that we took a sample of size 64 and the mean was 202, and we think, gee, that, you know, it's a pretty big sample. We think maybe that's a pretty good approximation of what the population mean is, right? But all we know is 202. We really can't describe how accurately we know that number. In other words, we can't predict from that what the real population mean is or how close to that number it is. However, having gotten that number and knowing what the sample size is and the standard deviation is, we know that based on this being a normal distribution, or being a large sample size, normal distribution, that we can predict that repeated samples of size 64 are going to be distributed a certain way around the population mean, right? So how are they going to, I don't know what I'm doing there. You know what it is? I'm brushing against the tablet. That's what I'm doing it. I get it with my arms. Okay, so we know that the way that repeated samples of size 64 are going to be distributed in the sample in the representation of the sample distribution, well, that's going to be the standard error is going to be equal to 20 divided by the square root of 64. 8 is going to be 2 and 1/2, right? 2 1/2, 2.5. That's going to be our standard error. That's our new standard deviation for means. Okay, so we say to ourselves, okay, so we were 95% certain that if we took a sample of size 64, that the value of that result would be between 5 and 5 below and 5 above, 2 standard deviations, below the true population mean and 2 above. So we're going to use that kind of bracket where the real population mean might be if this is the result we have from the sample. The way we're going to do that is we're going to calculate a confidence interval. In our case, a 95% confidence interval. Okay, so let's see. So my mean, X bar, I'm going to take my mean and I'm going to add and subtract the number of standard deviations, standard errors, because we're talking about a mean, number of standard errors that I need to add and subtract from that mean to capture the population within that range. Okay, so I could, if I use the empirical rule, I'd write 2 in here. If I use the real value from the Z table, I would write 1.96. And I think we beat this to death the last time, right? 1.96, 2.58, right? 99% is 2.58. 90% confidence is going to be 1.64, and so on. So we beat that pretty much to death. I'm just going to talk about 95% now. So now X bar, right, is how much? It's 202. Plus or minus 1.96 times the standard error, which is equal to 2.5, right? So we're 95% sure that the true population mean is going to be between 202 minus this margin of error and plus this margin of error. So let's actually work that out. I'd ask you guys to do it, but you're always too slow, so I'm impatient. Okay, so I'm going to put that into numbers. So I'm going to take 202 minus that confidence interval equals 197.1. I thought I put it in the spot where I'd get to it quickly. 202 plus my margin of error equals 206.9. Okay, that's we're 95% sure that the true population mean is between those two numbers. Does that mean we've always captured the true population mean? No, 5% of the time we're wrong, right? I mean, on the average, if we did it many times, 5% of the time we'd be wrong. 1 out of 20 times we would miss the true population mean outside of it. In this case, did we capture the population mean? Well, if it was the same problem we were talking about before, where the population mean was 200, yeah, it is between those two numbers. I wouldn't say we got lucky, right? 90%. We expect to be lucky. That's why we use 95%, right? If we're willing to take more of a risk of missing it, right? We could say we can make that narrower by using a 90% confidence interval, which would mean this number would be 1.64, which would make this margin of error that we're adding and subtracting a smaller number, so it would be a smaller range. If we are nervous and we want to be more confident, we could say we want a 99% confidence interval, in which case we would use 2.58, which would make this margin of error a bigger number. So we're adding and subtracting a bigger number, which would make this range for our confidence interval wider. So we're more confident that we actually captured it, right? So as we go, 99%, 95%, 90%, as our level of confidence goes up, as we want to be more confident, we start with a narrow range to a wider range to a very wide range, right? So this means that we're confident that it's really going to be captured between those two values. Okay, so let's look at this. Now, here's the elephant in the room. There's a big lie here, right? That big lie is that almost always we don't know what the standard deviation of the population is, right? So just like we don't know what the mean is, or we wouldn't, but if we knew what the mean and the standard deviation of the population, we would need statistics, right? We'd actually know those numbers. There's no reason for us to go any further, right? So in general, or almost always, we don't know what those two values are. So what does that mean to us? I'm going to take a sample. I'm going to take that same sample of size 64, okay? And I'm going to find the mean of those 64 people. Okay, in the mean, I'm going to get a little bit more adventurous here. I'm going to say it's 197. Okay, so now I'm going to say, you know, I don't know what sigma is. I don't know anything about this population. The reason why I'm sampling it is it's caused a whole new population. I've never heard of these people before, right? So how am I going to figure out what sigma is? How am I going to estimate what sigma is? Where would I get sigma from? The standard deviation of the population. Where do I get the mean? My estimate of the mean. Where do we get the estimate of the mean? From the mean of our sample, right? That's how we estimate the population mean from the mean of our sample. So how am I going to find out what the standard deviation of our population is? Get it from the sample too, right? In other words, the standard deviation of the sample. These randomly selected 64 people are going to have the same variability as the whole population. So they're going to mimic the population standard deviation. So the standard deviation of the sample is going to approximate the standard deviation of the population, right? So I'm going to say, for argument's sake, what did I say it was, 20? Let's say standard deviation of the sample turns out to be 18. What was it in the real population? It was 20, right? So what do we have here? We have two different things where we have uncertainty. Before, when we knew exactly how to lay out the spread of our sample means, we assumed that we knew what sigma was, right? Because then going from sigma to the standard error, right, is a formula, right? Probability tells us it has to be this way. If we take a bazillion samples, an infinite number of samples, this is the way those sample means are going to distribute it. That's math tells us that, right? But now we don't have that anymore. Now we're left with an approximation of the standard deviation of the population. So now that means we have two areas of uncertainty, not just the mean, but also the value of the population standard deviation. So now what does that tell us now? Remember before we were talking about, well, you know, I'm going to use population standard deviation just as I did for this, for the way I use sigma. I'm going to say that the standard error is equal to, instead of sigma, I'm going to say the standard deviation of the sample, which is the population, approximates the population, divided by the square root of the sample size. So that's 18 over the square root of the sample size, which is 64, which is square root of 64, which is 8 into 18 is 2 and 8, what was it, 2.25, right? 2.25, right? Now, we know that's not really true, don't we? It's a little bit of an error in there. It was really 2.5. And if we knew what the population was, it would have come out 2.5. Sigma for the population would come out 2.5. So now we got a problem. We got a problem. We want to construct a 95% confidence interval, which would have been easy before. We would have just used X bar plus or minus 1.96 times the standard error. right? And we would have got a mathematical approximation. We would have had a reliable prediction of what our certainty was of capturing the population mean because we knew what sigma was. But now we're not so sure about this. We're not positive about this. We don't know it perfectly anymore, do we? There's a certain amount of extra error in there. So if I want this to really be a 95% confidence interval, if I knew sigma and the confidence interval was from here to here, let's say 197 to 203, and I knew sigma, well, now I'm not so sure about sigma. So what do you think I have to do to that range in order to keep my confidence level at 95%? What do I have to do to that range? I think it's in here, but now I'm not so sure. So in order to accommodate the fact I'm not so sure, I got to make it what? Wider, right? So instead of 1.96, I'm going to use a different value, right? I'm going to use a larger value. So instead of a z-score, I'm going to use a t-score. And just like the z-score for sigma, we use the sample size to give us an idea of what our standard error is going to be. Well, if I have a large sample, my uncertainty is less for my estimation of what standard deviation is than if I have a small sample. There's more uncertainty. So we need to figure out what should I use instead of 1.96 to accommodate the uncertainty that I've put into this thing by using the sample standard deviation instead of the population standard deviation. So let's take a look at the t-table and get a look at how that works to help us out with that. Now, you can use one in a textbook. We also have one that's online from Agresti. They look pretty much identical. The one from the book introduces a little bit of a kind of a twist with showing the areas when you show the areas of the distribution. Okay, so this table says that here's the confidence interval at the top, like if you want to be 95% certain, right? This is the column you want to use. Well, when we talk about being 95% certain, we're talking about that confidence interval means that we could miss by 2.5% on the bottom, lower range, 2.5% on the top, right? So the way that they describe a 95% confidence interval is by describing it as the right tail probability. The right tail probability is 2.5%. So that means there's 2.5% on the right side, but there's also 2.5% on the left side. So that's 95%, 95% confidence. That's a 5% chance of being wrong, which is a 95% confidence interval. So that's the way they're describing that there. So if I wanted a 90% confidence interval, that would be 5% on the left, 5% on the right. So here in this table, it would be described as a right tail probability of 5%. Would give us a 90% confidence. So if I look over here, the 5%, yeah, indeed, that's 90%. So you kind of use a little bit of judgment here. That's really what it's describing here. So 95% confidence interval is what we're after. Okay, so let's say that our sample size is, yes. Did I say calibrate? Okay. Calculate calculated standard deviation. Oh, the sample probably the sample standard deviation. In other words, the standard deviation that we're using for the population is an approximation based on the sample that we've taken, those 64 people that we've taken. We're saying that approximates sigma, but it's not exactly sigma. That's why we need to use the t-score, okay, to make up for that uncertainty that we've introduced by using our sample standard deviation instead of sigma. So let's go here and take a look at this. So the degrees of freedom really is just a way of describing the sample size, right? One of the ways you can kind of look at degrees of freedom, if I take a single number, right? If I take a sample of one person, right, and their cholesterol is 178, right? Well, what do I know about the variability? I know nothing, right? Yeah, so yeah, it's only one person. So there's no degrees of freedom there. You don't know anything about the variability. If I take two people, well, now I got 1 degree of freedom. I have this person and this person, one person that I can choose from, right? If I have 100 people, that's 99 degrees of freedom, right? So the degrees of freedom is just a sample size minus 1. Okay, so let's take a look at the bottom of this table first. I'm going to go right. I'm going to stick with this 95% confidence. Let's go all the way down to the bottom. The value on the bottom is 1.96. That's what comes out of our Z table for a 95% confidence interval. What's the sample size we're dealing with here? It's an infinite sample size. So in other words, this T table, if you're working with a super large sample size or an infinite sample size, right? Then the T score and the Z score, the T value and the Z value are the same thing, right? That you're going to use the same number. Well, how about if you take a sample size of 5? That would be 4 degrees of freedom. So the Z score that you would be using is 2.776. So you're going to use that instead of 1.96, right? So when you calculate your confidence intervals, what does that mean? You're confident your margin of error is going to be bigger. You're going to be adding and subtracting a bigger number, and your 95% confidence interval is going to be wider. That's because you have such a small sample size. You can't use Z, can't use the Z table, because the Z table would have told you 1.96, and it wouldn't take into consideration the extra uncertainty that you injected by using a small sample size to predict the population standard deviation. So what happens is the sample size gets bigger. If we have a sample size of 7, what will we be using? 2.365. Getting closer. How about 10? 2.228. How about 15? 2.13. How about 20? 2.06. So what's happening here? What is this getting closer and closer to as the sample size goes up? Bingo. Let's say a sample size of 30. 2.04. Sample size of 40. 2.02. Getting really close. That's why, for instance, you might say to yourself, you know, for our purposes, we might say, you know, if it's a sample size of 30 or 40 or bigger, maybe we'll say to ourselves, I'm not going to go to the table. I'm just going to use 1.96. Why? How can you justify that? Because the sample size is so large that the T value that you would use is going to be close to 1.96 anyway. It's not going to be the same, but it's going to be close to it. So if you're willing to introduce that amount of error, right, that possibility of error, difference between 2.02, let's say, and 1.96, you could consider 35 or 40 a large sample and just use 1.96. If you're not comfortable with that, you might say, you know, in my book, I think 100 is what you should consider as a large sample. And that would be 1.98, which is really close to 1.96. I mean, most people would be happy with that. There's more to that as well. There's more to this because in central limit theorem, remember, a lot of times we're taking advantage of the central limit theorem because the original population doesn't have to be perfectly normal if we're looking at repeated samples in that population. It turns out that if you take repeated samples from a population that is skewed or not completely normal, the distribution of the samples becomes more normal. It becomes closer to a normal distribution. So it really helps us out. We can apply this a lot more cases than the few cases where you might have a population with a perfectly normal distribution that you would have to depend on. So this really helps us out a lot. The thing is that just like the T-score getting closer and closer to the Z-score, the larger the sample size, the bigger excursion that you can tolerate from a non-normal distribution to apply the central limit theorem, right? So the bigger the sample size is, the more it helps you. Allow yourself to do calculations on the assumption that the sample distribution is going to be normal. Okay, so it helps us out, right? So now let's go back here and let's do that sample we just looked at, that problem we just looking at. Okay, so I'm going to actually, let's do this. Okay, so X bar plus or minus Now it's going to be the t-score instead of the z-score. Why is it going to be t-score? Because I don't know the population, I don't know sigma, I only know standard deviation. So it's going to be t times standard error. And our t for this case is going to be 0.05, an error of 5%, 0.05 or 95% confidence. Okay, so what is this going to be equal to? Well, first, let's start with x bar. Our sample mean came out to be 197, plus or minus the value for t that we're going to use for a 95% confidence interval. Well, what's that going to be? So for sample size of 64, what am I using? 63, right? Well, I don't really have 63 here. So the closest I have is, I'm going to say, what's that, 2.0? 2.0. So I'm going to use 2.0 instead of 1.96. 2.0 times my standard error. And what's my standard error going to be equal to? It's going to be equal to the standard deviation of my population, which is really being estimated by the standard deviation of the sample. It's going to be 18 over the square root of the sample size, which is going to be 64 is 8, right? So it's going to be 197 plus or minus 2 times 2.25, or 197 plus or minus 2 times that is going to be 4.5. So it's going to be 192.5 to 201.5. I get that right? Right. So had we known the population standard deviation, right, we would have used, instead of 2, we would have used 1.96 and we would have been narrower. If this sample size, instead of 64, if that sample size had been 25, what would have happened to the range here? Would it be wider or narrower? Wider. Why is it going to be wider? Because instead of using 2.0, you might be using, I'm going to guess, 2.3. So the margin of error is going to be bigger, getting extracting a bigger number. So, and by doing that, you make up for that uncertainty that you introduce by using a smaller sample as your estimate of the population standard deviation. Okay, let's open up a file from Blackboard and you guys can try an example of this. Let's see. There it is. How are we doing online? Okay. Oh, good. Okay. It's a lot harder, right? Typing it in there, especially because you have a limit on the number of characters. Oh, maybe not on here. You have a limit on the number of characters you can type in, right? Because you do on YouTube. In YouTube, I think it's 200 characters you can type into the chat box. But on here, we're on GoToMeeting here, so it may be different. It was annoying because it didn't stop you. There was a little counter at the bottom where it counted the letters, but it didn't like turn red or like vibrate or something like that when you got over. So you type it and you have 300 characters in there, and then you try to hit enter, it just refused to enter, so you have to backtrack. Let's see, here we go. Okay. Oh, that's not what I wanted. Weekly materials. Okay, that's us. Okay, let's see which one I want here. Keep this one. What I'm interested in, that's probably going to be proportions. Oh, that's a proportion. Takes a while before Word will let me edit once it starts up. I think Microsoft is doing this on purpose to get me to upgrade. There we go. Okay. Oops, I think I deleted the wrong one. Okay, let's start with the second problem here. You randomly sample 40 New York City pubs on St. Patrick's Day and find that they inventory an average of 42 types of beer. You calculate the standard deviation for these pubs from your study data and find it to be 6.3 beers. So what's our mean here? What's X bar here? 42, right? And what is our standard deviation for the population here? Well, we don't know the population standard deviation. So what are we going to use in place of that? It's the standard deviation for the 42, for the 40 bars that we sampled. And that standard deviation for those 40 values is 6.3. So our estimate, our standard deviation for the sample is 6.3. Our standard deviation, our mean for the sample is 42, right? And we don't know what X bar, we don't know what mu is, and we don't know what sigma is. Well, we're going to use 40 to estimate our population standard deviation, and we're going to use 6.3 to estimate our, 42 to estimate our mean, and 6.3 to estimate our population standard deviation. Okay, what's our sample size? Sample size was 40. Okay, so 40 is, let's see, that's actually, I'm wrong there, that's 42. Let's just say 42. 42 is mu or X bar? X bar. Okay, good. 6.3 is sigma or standard deviation. Bingo. Right, great. Calculate the standard error for repeated samples of the population of size 40. So go ahead and calculate it. I put sigma in there, but we know now we're going to substitute our estimated sigma for that. And our sample size was 20. So what do you guys get? What do you get for the standard error? I got a prediction yet? Anybody figure it out yet? Before I hit enter? Okay, let's see. Let's see if you got the same thing I got. How much was that? Okay, 0.992. Let's see what I got. Okay, I got 0.996. Maybe I'm wrong. Hang on a second. Let me clear this. And I'll go through the process of how I got this. The first thing it's going to be my standard deviation is 6.3, and I'm going to divide that by the square root of my sample size, which was 40. Okay, so first thing I'm going to do is I'm going to clear up memory, and I'm going to calculate the square root of 40. 40, square root of 40. I'm going to put that into memory, and then I'm going to clear my register here. Okay, then I'm going to take my standard deviation, 6.3, divided by my square root of my sample size, which was 6.32, and that's equal to 0.996. Okay. Did you use 42 by any chance? I think 42 was the average, right? I'm sorry I made them so close. but maybe it's possible. Or you just might be, might not, if you're doing it by hand, you may not be getting as many decimal places as I'm getting. So basically, the standard error is pretty close to 1.996. I'm going to call it 1 for argument's sake. Okay? So I'm going to go back. Actually, I'm going to go open a sheet of paper here. Let's look at that. Refresh sheet. Well, what is this? Okay, X bar plus or minus. Now, here's a problem here. Am I going to use Z or am I going to use the t-value? I'm going to use the t-value, right? Because I don't know. I don't know what the population standard deviation is, and it's not a large. It's borderline. I could, in some cases, you might argue it's a large sample. Sample size was 40, but I'm going to say, I'm not going to consider that a large sample. Sample size equal to 40. T times my standard error. Okay, so what was X bar? X bar was 42 plus or minus the value of T. Let's see what we're going to use as the value of T. Right, so which column am I going into? I'm going into the column that has a right tail probability of 2.5%, right? Because 2.5% on that tail, 2.5% on this tail is 5%, which is my 95% confidence interval. And I'm going to go down to degrees of freedom 39. Now it doesn't have 39, I'm going to use 40. And 40 is 2.02. So I'm going to go back. So my t-value for 95%, 2.5% in each tail, is 2.02, and my standard error was equal to, I'm actually going to put 0.996. Now, if I had known sigma, right, then we would have used 1.96 here. Okay. And if it were a sample size of 100, I might have said to myself, I'm not going to bother to go to the Z table. I'm just going to use 1.96 because I know the p-value is going to be pretty close. It's going to be 1.98 actually. Right? Okay, so let's figure this out. Okay, so I have 2.02 times 0.996 equals, and I'm going to clear memory and I'm going to put this into memory. Clear that out of there. So I'm going to take 42 minus my margin of error, which I've just calculated, and that's going to be equal to 39.9899 actually, right? And 42 plus my margin of error. And, whoops, I missed. 42 plus. Computers make the worst calculators. Plus. Is equal to 44. Right? Whatever that came. What was that? I guess 40 to 44 basically. Okay. And why did we use T instead of Z? Because the small sample size and not knowing what sigma was forced us to do that. Let's do it for a proportion. See what happens if we work with a proportion instead. Okay. I think the other one had a different exercise there. Did it? Okay, let's take a look at this one. Okay, suppose we want to know the true population proportion of Irish Americans who approve of wider representation of all groups in the St. Patrick's Day parade. This is not a debate anymore. This used to be a big debate 20 years ago or something like that. It's not even a debate anymore. In 2000, the parade committee asked a random sample of Irish American parade participants if they approved of wider representation of all groups in the parade. Out of 1,381 respondents, 496 of them approved. What can we say about the true population proportion, P, not P cap, but P, about the true population proportion? Well, we get a value from this, right? What's that value going to be? See what it's going to be. What proportion of our sample said that they were in favor of a wider representation? How many people did we sample? 1,381, and 496 of them said they approved. So 496 divided by 1,381, and that's equal to 0.359, about 36%. Right? So what is our p-value for the population? Do we know what p is for the population? So everybody takes part in the parade. No, we don't. So we know, what is this instead of p? How do we signify p cap, right? Use p cap. This is the sample proportion. So 36% of our sample said they favored wider representation, right? Do we know what our population proportion is? No, we won't know it unless we ask everybody that attended the parade that day, right? So we don't know what it is. We don't know how accurate this 36% is. But what we can predict is we can establish an interval within which we're 95% sure the true population proportion is going to be living. Okay, so let's calculate that. Okay, so just like before, I'm gonna call it 36%. By the way, yeah. Come on, open up. There we go. Okay, so anybody remember what the numbers were? 490 what? 496 over 1381. Okay, and that came out to be about 0.36. So P cap, right, our sample proportion is equal to 0.36. So P cap approximates the population proportion, right? Now we got a problem. You know, if I want to have a confidence interval, if I want to calculate confidence interval, this is our point estimate of what the mean is. But now I need a proportion is, but now I need a range that I'm going to develop that I'm 95% sure the true population proportion resides in. So I'm going to say P cap plus or minus. And so now I got to choose either T or Z. What am I going to choose here? T or Z? Why T? What's the sample size? Sample size gigantic, right? In most cases where proportions are involved, your sample size is going to be quite large, right? Remember we had that rule over that says, you know, a loose rule that says over 30 is a large sample, right? Well, we're going to use that here too. And we're going to say that we want a sample size of at least 30, except we got a special rule. We're going to say that both sides of the proportion has to be greater than 15. So, right. So in other words, if it turned out to be 14 out of 1,381, even though that's a very large sample, you know, the number of people in favor versus the total number of people, or against versus the total number of people, doesn't exceed 15. So I'm not gonna say my sample size is large enough, right? But in this case, it's 496 versus 700 and something or something like that didn't improve, right? So I can go ahead and calculate my confidence interval, and I don't have to bother with T. I can use Z, and that's going to happen most of the case, almost all cases, when you deal with a proportion, because you're going to be dealing with much larger sample size. So it's going to be P cap plus or minus Z times your standard error. How do we calculate standard error for a proportion? Anybody remember? Square root of P, right? P, the population proportion, times 1 minus the population proportion, right, over the sample size. And just like before, standard error becomes smaller as the sample size becomes larger, right, because it's on the bottom of the fraction. Now, we don't know what the population proportion is, so we're stuck using what? P cap, right? So it's going to be equal to the square root of, if we knew the population proportion, we would use that, right? P cap is going to be equal to 0.36 times 0.64 over the sample size, which was 1,381. So what's our what is our standard error going to be equal to? Yes. Oh my goodness! I didn't know that was hanging over there. How's that? In fact, yeah. Okay, that's better, right? I'll try and avoid that. Okay, so that's equal to, let's see. Let's get my calculator out. So that is equal to, let me get this over here. Clear. Okay, it is 0.36 times 0.64 equals this, divided by 1381 equals, it looks like a tiny number, but you got to take square root of it, right? And square root's going to, when you do a fraction, square root's going to be a bigger number. Square root, this comes out to be 0.013, 1.3% or 0.013. So how are we going to use that? We're going to go back here and say P cap is 0.36 plus or minus our z-score, which is 1.96, times our standard error, which is 0.013, 1.3%. So I'm going to just call this 2 so I can go through this quickly. It's going to be 0.36 plus or minus 2 times this is going to be 0.026, 2.6%. So my 95% confidence interval here is going to be 0.36 with minus 2.6%, which is going to be 0.334 to 33.4% to 38.386, 38.6%. Right? So I'm 95% sure that the true population proportion, P, not P cap, true population proportion is between these two numbers. What does that tell you about the true population proportion? Does it tell you that you're 95% sure that the true population proportion is in favor of wider representation or against wider representation? You're 95% sure the true population proportion of people that are in favor is between these two numbers. So 50% is bigger than this, right? So it looks like the majority are not in favor of it, right? Are you sure they're not? Well, we're at least 95% sure, right? So that's the beginning of where we're going to apply this, right? We're going to, this confidence interval can kind of tell us, can start, we're going to use it differently. You don't really use it this way. But now that we know, we're 95% sure the true population mean is between these two numbers. If we take that and compare it to another number, we can say we're 95% sure that the population mean is different than that other number. Or if that other number is within the confidence interval, so that confidence in 95% confidence interval says that the true cholesterol level of people in Michigan is between 160, 192 and 208. And I say to yourself, well, in France, they test everybody's cholesterol. And in France, the true population mean is 216. Well, it's outside of our confidence interval for people in Michigan. So, gee, I'm pretty sure that people in Michigan have a lower cholesterol level than people in France because I'm comparing it to the known population of France. But if I said my confidence interval was 192 to 208, and the true population mean for cholesterol in France is 204, well, it could be the same, right? We don't know what the true population mean is for people in Michigan. We only know that range is likely to contain it. So if it's 204 and we're comparing it to people in France, and they're 204. We're no longer 95% sure they're different anymore, right? Because it isn't outside of our confidence. Are we going to use it that way? Kind of yes and no. We're going to twist this around next week, and we're going to start to talk about something called the t-test. Just like we use the t-distribution here, right? We're going to look at that t-test. What is that t-value and the z-value? What do they really represent? They represent the number of standard deviations that values are apart. So when I say a z-score of 1.96, I'm talking about 1.96 standard deviations to the left of the mean, 1.96 standard deviations to the right. When I talk about a t-value of 2.0, I'm talking about 2 standard deviations, one direction or another direction, right? Or one t-score of 2.5, 2.5 standard deviations apart. So next week, we're going to start to talk about situations where we'll look at two samples, for instance, right? We're going to start a little simpler than that. We look at 2 samples and we see that these 2 samples, that one has a 95% confidence interval for the true mean of that population A of 190 to 200. And the other population has a 95% confidence interval of 205 to 215. And they don't overlap. So we're 95% sure that this group, that this population has a mean here, and this population has a mean here. So they don't overlap, so we're 95% sure that they're different, kind of. But if they do overlap, right, it is possible it's impossible to say with 95% certainty that they're really different. That's kind of a messy way to do that. What we're going to do instead is we're going to look at the mean of one group and the mean of the other group, and we're going to try and predict how many z-scores, how many t-scores or z-scores that they are apart. And if they're 1.96, if they're both large samples, and they're 1.96 standard deviations apart, then we can say, we're 95% sure that those 2 values came from 2 different populations with 2 different means. Okay, so we're going to twist this around a little bit. But you can almost start to see how this is going to work, how we're going to use our confidence, the level of confidence that we have in what we know about the means, to be able to tell whether when we compare populations or samples, whether or not we have enough confidence to say that they're different, or if the values are too close together and the variability is too great, and we can't say that they're different with the level of certainty that we want. Okay, so how are we doing on time here? So we got a little bit of time left. You guys had some questions about the homework? Is that still around? Did we resolve that, or should I open that up? Okay. Oh, I got the pencil in there. Okay, hang on a second here. Here we go. So which homework was the first one that was an issue? 3A. Okay, which problem were we interested in? We were looking at the, okay, I know which one this is. This one, question 15, question 10 rather. Is that where we're starting with this? That like where we went off the rails a little bit. The probability that an infant is born prematurely in Mexico is 0.15. That's population. That's population parameter, right? Probability of all the infants among all the infants is 0.15. What is the standard deviation, standard error for the proportion of premature births from samples of population of size 25? So we're looking for the standard error for this for 0.15. So let's see, standard error is going to be equal to the square root of p times 1 minus p divided by n. So we actually know what p is here this time, right, for the population. So it's 0.15, right, times, let's see, 0.15 times 0.85 divided by 25. So if I can remember that well enough to not have to refer to it again. Clear? Okay, 0.15 times 0.85 divided by the sample size, which was 25, equal to this. I take square root of that. So my standard error for repeated samples is going to be 0.07. Now, all that's telling us is what the true standard error is going to be if we take repeated samples of that size, right? But we know what the population proportion is. Now, the next two problems. The problem with the next two is I didn't tell you what proportion to use. Okay, but it refers to the previous problem. So instead of asking you on the next two problems, I could have said that we took a sample and the proportion was 0.15 from our sample of size such and such, right? I could have said that here. In other words, I said the sample size is going to be 625. And I could have said that in that sample of size 625, that the proportion within those 625 people was 15% of the infants in that group were premature births. And you don't know what P is for the population, right? I could have said that, in which case you would have calculated the confidence interval, right? In other words, you would have said 0.15 plus or minus, right, 1.96 times the standard error, except instead of using 625, instead of 25, you would have calculated 625. And you would have got a lower number and a higher number. I kind of twisted it a little bit, and what I told you was that you know the population proportion is 0.15. That's the population. So I asked you instead, we would expect 95% of samples of 625 to have a proportion in the sample between this number and this number. I'm asking the same question, right? So like in other words, if I know the population proportion is 0.15, right? If you can use the standard error to predict what the range would be for 95% of repeated samples of that size. So it's the same thing as asking you the 95% confidence interval, except this time you're describing the sample distribution. You're telling me that that sample distribution for all the possible samples of size 625 is going to have a proportion for the samples between this value and this value. In other words, 0.15 plus or minus 1.96 times the standard error. That makes sense to you? Maybe if I describe it as a sample mean, it'll make more sense to you. If I, plus or minus 1.96 times the standard error, the square root of P times 1 minus P over N. Maybe it'll make more sense to you if I describe it as a mean. Okay. Actually, let me draw it. I think maybe drawing it might help a bit better. Okay, I put that there because I thought it would help, give you a different way to look at this, help you wrap your heads around this. Okay, so the true population proportion, P, is equal to 0.15. Notice there's no cap on that. We're talking about the true population proportion, right? So if I take samples of size 625 from the population, and I draw a distribution that represents all the possible samples, I take infinite number of samples over and over again. Sometimes I'll get 0.12, sometimes I get 0.18. But what is the distribution of those samples of size 625? Well, on average, they're going to come out to be 0.15. Just like we would if we were talking about a mean, right? Okay, but what about the spread? How spread out are they? Well, that's standard deviation. If I calculate that standard error, square root of P times 1 minus P, right, over N. If I calculate that, that's going to tell me my standard deviation, right, my standard error for repeated samples of size 625. So let's calculate that. That's equal to the square root of 0.15 times 0.85 over 625, and we just did that, right? Did that come out to be? Did we do that? I didn't do that. Okay. Let's actually do that. Uh, 0.15, 0.15 times 0.5 divided by 625 equals this, times root of that, comes out to be 0.014. That comes out to be 0.014. So so if I go 2 standard deviations to the left of 0.15 and 2 standard deviations to the right of 0.015, or more accurately 1.96 standard deviations to the left and 1.96 standard deviations to the right, what's that going to tell me? That's going to tell me that 95% of the time, if you take a sample of size 625 from this population, it's going to be between those two numbers. And what's that going to be? Well, that's going to be 1.96 times 0.014. I'm just going to call it 2 for our purposes. That's going to become 0.028, right? So if I add that to 0.15, that's going to be 0.178. If I subtract it, it's going to be 0.122, right? So 95% of my samples of size 625 are going to be between 0.122 and 0.178. So I didn't ask you what the confidence interval was. I don't need to because I know what the mean is for the population. I asked you if I took a step back and I repeatedly over and over and over again took samples of size 625 from this population, what would be the range of proportions that I would get 95% of the time? Well, 2.5% of the time, I would get a value less than 0.122. And 2.5% of the time, I get a value more than 178. I could have turned this around and said, hey, listen, I took a sample size of 625, and I got a value of p cap is 0.15. In that case, I might have asked you, what's a 95% confidence interval for your true proportion in this population? In which case, you would have looked at this the way we normally look at this for a confidence interval, p cap plus or minus 1.96 times the standard error. And that would have given you your 95% confidence interval for the mean. Except you probably wouldn't have 0.14, you might have had 0.13 or 0.16. You wouldn't have had the population proportion. That's why you do the confidence interval, because you don't know what P is. If you know what P is, you can predict what the distribution of your sample is going to be. Okay? If you don't know what P is, you can use the same principle to predict the range for where the true population proportion would be. So I kind of turned it around on that problem, so that you would to get you to describe the range that you would expect 95% of the sample proportions to be. Yes. It isn't really. It's not. If I were to say that the proportion for my sample was 0.15, exactly the same as the population proportion, it turns out to be the same numbers, right? But my sample proportion is not really going to be 0.15. It might be 0.14, for instance, right? But the real true population proportion is here, right? And it just happens that this is the range that when we're looking at the confidence interval, we're predicting a range that we're hoping will capture that true population proportion, because we don't know what the true population proportion is going to start. If I were to do it with means, it might be a little bit easier to understand if I did it with a mean. Okay, you take a sample size 100, right? And I say to you that X bar is equal to 50, right? And in this case, I'm going to tell you that the standard deviation of the population is equal to I don't know, let's call it 10. Okay? If I were to ask you, if you took repeated samples of size 100, how would those samples be distributed? Those sample means be distributed. Actually, mu. I'm telling you mu, sigma, and the sample size. How would those sample sizes be distributed? Okay. Well, you know that mu 50 is going to be in the middle, right? For repeated samples of size 100, and the standard deviation of the population is 10. But our distribution of samples is not going to be that wide. It's going to be narrower. It's going to be my standard error, which is 10 divided by the square root of 100, which is 10 is equal to 1. So 95% of my, if I took a sample of size 100, 95% of the time, I would get a value between 48 and 52, right? 2 times the standard error, right? So I would get a value between these two, right? That's what that problem was asking. That problem was asking you to give you the range within which you would expect to get 90, given that sample size and given that you know what P was, what range would you expect to get your proportions when you take repeated samples, right? So it's asking you the same thing as this. On the other hand, if you didn't know what mu was and all you knew was X bar and it turned out to be 48, right? You would then use that plus or minus 1.96, let's say, if we know sigma, plus or minus 1.96, the sample size, same sigma times 1, it's going to be 48 plus or minus 2, which would be 46 to 50, and you would use it in a way that you would say, I'm 95% sure the true population mean is between these two values. But notice this one describes the real, based on this mu being 50, this describes the way that repeated samples would look if you took them over and over many, many times. This represents your one sample and what you can deduce about where the real mean is from the confidence interval. I'm losing my voice. I'm going to stop. Okay, well, any other questions?